Okay, so welcome back to another video. So in today's video we have another infinite sum dealing with the harmonic numbers. So h sub n divided by, and now including an n factorial. So I should write what defines a harmonic number. Harmonic numbers are basically, it's the partial sum of the reciprocals at that n, the max index at n. So that means h sub n is equal to, so our index starts from k is equal to 1 all the way up to n of 1 over k. So basically we have a sum inside of a sum. And it was basically just like the same video I did back in, I believe, March, where instead that the denominator is basically 2 to the power n multiplied by n squared. So since we have an n factorial, so things are going to be completely different in terms of trying to evaluate this infinite sum. So what I'm going to start out by doing from here is that I'm actually going to define our, we're going to consider our generating function f of x, and we're going to let that be defined as the infinite sum with h sub n multiplied with x to the power n, and then divided by n factorial. We're also going to use the following recursive relation that h sub n is actually equal to h sub n plus 1, and then subtract that with 1 divided by n plus 1. You can see this since h sub n and then h sub n plus 1, so we increment our term by 1 more, and if you evaluate this, you get evaluate 1 over k as 1 over n plus 1, and you're subtracting that term, returning back to what defines just the harmonic number is at the nth term. So we'll be using that to our discretion, and then manipulate with our generating function. Okay, so now this means that, right here should be good. That means f of x is actually just equal to, so now this is still the infinite sum. Then we're going to replace our h sub n with this recursive relation over here. So then we have h sub n plus 1 minus 1 over n plus 1. Then that's multiplied by x to the power n. Not the x sub n, as we're not dealing with sequences here in this case. And then of course divide this by n factorial. Right, and now we can continue manipulating some stuff. Well, simply we can actually distribute the x to the power n into our recursive relation. So this is, then we have h sub n plus 1 multiplied by x to the power n, and then subtract that with x to the power n divided by n plus 1. This is still being divided by n factorial. We can actually split this into two sums, and also note that for here, well, actually before I get to that, let's actually write the first sum where we after splitting this up. So the first one we would have is just h sub n plus 1, and then x to the power n divided by n factorial. Then we need to subtract with, so we have x sub n divided by n plus 1 divided by n factorial. So note that, here let's write this let's write this in red. So note that using the rule that if I say x sub n, or x to the power n divided by n plus 1, that can be the same thing, that's also rewritten with multiply with 1 divided by n factorial. So notice n factorial is decreasing by 1, so it's n then time with the products, of course. So n times n minus 1 times n minus 2. So if you go backwards, you add 1. So really you can actually say that this is actually n plus 1 factorial. We start there, and then we decrease the increment by 1. So we start with n plus 1, then times n minus 1. So we can rewrite that as n plus 1 factorial. So that means I can replace that for over here. So of course this will be x to the power n divided by n plus 1 factorial, but we're splitting this into two sums, so I'll write this as another infinite sum. So let's see, n equals 1. Then this will be x to the power n divided by n plus 1 factorial. Now what I can do from here is I'm going to readjust our indexes for both of these sums. You're going to see eventually later why we do this. But we're going to start at our index n equals 2. Alright, so if we start at 2, that means we have to change all of the indices over here from our function. So if we start at 2, that means this will have to be h sub n, and then x to the power n subtract 1, and then this is being divided by n minus 1 factorial. Now if I subtract this and we change this to our index starting n is equal to 2, then from here this will be x to the power n minus 1, and then this is being divided by n factorial. Alright, so now on to our two little notes that we want to analyze between these two sums. So the first one, let's actually write this with red. Let me actually write this with red this time. So here are the following notes that we can analyze here. So the first one, h sub n then times to the power x to the power n minus 1, then divided by n minus 1 factorial, right? We can actually rewrite our, well, really what I can do is I can actually multiply and divide an n. Well, what that will do is that will actually readjust this factorial over here. So now we'll be starting with n factorial instead of n minus 1. As you can see that we actually adjust by 1. Then we have n times n, h sub n, then x to the power n minus 1. Then we start with n factorial, right? But now next thing I can do here is that I can actually change our index. So really I can start this, I'm going back to starting with n is equal to 1. Now of course I can actually just write this back as the same as it is. So h sub n, x minus 1 divided by n factorial. But then that would have to mean that I would have to evaluate this at 1 in order to preserve this equality from over here. So if I were to set n is equal to 1 and plug this over here, so let's see, that will be, so if I plug 1 over here, then it's just x to the power 0, that's just 1, then h sub n, so if I plug 1 here, so that's just 1, so the whole thing just becomes 1, and I would have to subtract this, and then subtract it, and then we get minus 1 over here. Alright, so that's the first note. Now the second note is, now we're going to analyze this infinite sum. So next is the infinite sum from starting from n is equal to 2. Then this is x to the power n minus 1, then divided by n factorial. Before I jump into here, let's actually do one more quick analysis. You'll see that since we were given that since we rewrote this and we achieved that it's n times the harmonic number n and then x to the power n minus 1 divided by n factorial minus 1, excluding the minus 1 for a sec, but you'll see that if I were to take the derivative of our f of x function over here, you'll see that, so this, I subtract 1, then that means, well, first I would have to move the n to the front and then subtract 1 the degree, and you'll see that that matches with this function over here, this, well, infinite sum, really. Then I can actually rewrite this as saying this is f prime of x, and then subtract that with 1. Alright, now that's good. Okay, now the next thing is this note here. Now, what I can do from here is that, of course, I can just readjust our index. This time I'll actually start the index as n is equal to 0. And that means if I were to readjust this, then, well, it's not really readjusting. Simply, I can just rewrite the same function, n minus 1, then divided by n factorial. But of course, I would have to evaluate this for n equals 0 and n equals 1, and then subtract the terms from the opposite side over here. Then if I plug, so that means if I plug 0, then this will just be minus, well, really, if I could just plug 0 into here, then that means I'll just get 1 over x, and then if I plug 1, so I'll just get 1. So yeah, there we go. So that's another thing we can do. So now from here, this means I could actually substitute our two functions from over here. So now this we have, so if I'll just rewrite the same thing, so this is the infinite sum, starting from n is equal to 2 of h sub n and then x to the power n minus 1, divide this by n minus 1 factorial, subtract this with the infinite sum, n is equal to 2 of x to the power n minus 1, then divided by n factorial. So that means I would have that. So now I switch this to the red. How about this? I'll draw the parentheses here first, and then we can fill in the gaps of what we have. So this means we would have a f prime of x minus 1 and then I'll subtract this with our substitution over here. And really, now that we have this, you can see that this is actually the power series of e to the x, well, really the Maclaurin series of e to the power x, and then divide by x. I should have wrote that down earlier, but that's fine. I stated it here, so that's okay. So 1 over x, and then minus 1. Okay, and then now from here, we could just perform the easy calculation over here. And so far, this is saying that this is for f of x is equal to this. So now we have, so this is f of x, and that's set that it's equal to, that will be f prime of x, so minus 1, and then minus 1, that cancels. So then minus, and I'm gonna put this in parentheses just for now. And so then this will be, so they have the same denominator, so I can just put this under one fraction. So it's e to the power x minus 1, and then divided by x. And here's the really interesting thing. Now, if I were to rearrange the equation just a bit, so if I'll keep all the f of x's on one side, and then, well, with the derivative of that, of course. So I'll subtract this with f of x, and then I'll keep this as, so see, I'll add the other side. So that means this will be e to the x minus 1, and then divided by x. This is cool because you see that this is actually in the form of a first order linear equation. And well, the formula is defined as the standard formula for a linear equation is defined as, you know, dy over dx, and then plus some function p of x times y, and then that's just equal to q of x. So standard way to solve this is you want to find your integrating factor, which means it's just e to the power the derivative of, or the integral of your p of x, and then substitute that back in, and then you'll see that you can the product forms is in a form of the product together. If you integrate that, it's like it's integrating the derivative of that product, and so you have to integrate the other side. So that's pretty much the standard way to solve these. So not so bad from here. So now I'll actually use the integrating factor here, int, and then factor. So that means we have our so our p of x in this case is -1. So I'll write that. So that means our integrating factor would have to be mu of x in this case is equal to e, and then to the power of the integral of -1 dx. But I'll just write this as negative, and then the integral of dx, and so that's just equal to e to the negative x. So now from here, I'll just multiply e to the negative x to both sides of the equation. Let's see, it's right here. Good. I apologize about the light. Yeah, right here should be fine. Or here. Over here. Okay, so I'll multiply e to the negative x to both sides of the equation. So that means we have e to the negative x, then f prime of x, subtract that with e to the negative x, f of x, and then that's just equal to, so let's see, if you multiply e to the negative x, then that means I would have to get 1 and then subtract with e to the negative x, and then it's just divided by x still. Okay, and now you see that now I can actually take the integral of what you see is that this is the product rule, so it's the derivative of the product. So I can write this as d over dx, and then I'll just write this as mu of x multiplied with f of x dx, and then of course I have to set this equal to the integral of 1 minus e to the negative x divided by x dx. Now you see from here on the right hand side, I'll go back to, I'm going to go to blue for this. So as you can see, the integral 1 minus e to the negative x, x dx, that could be rewritten as 1 over x dx, and then subtract that with e to the negative x divided by x dx. And then here's the interesting thing about this indefinite integral. So this indefinite integral is actually, if you integrate this, you'll actually get the you'll actually get the special function known as the exponential integral. So that means, well, specifically since this is at negative x, so this will be e to the ei of negative x is equal to the indefinite integral e to the negative x dx. Now that would have to mean that if I want to cancel this integral, basically I could just take the derivative of both sides, which is just basically kind of like, well, I wouldn't say really exactly, but it's almost thinking in the ways of doing the fundamental theorem of calculus, just to get rid of the integral sign by differentiating that integral. So that means d over dx is equal to this, or d over dx of ei of negative x is equal to, so I'll write it like this. So if I integrate this, okay, so we know that 1 over x dx, that's just basically the natural log of x. And if I integrate this left-hand side, we're just going to be left with e to the negative x and then f of x. And we set that equal to the natural log of x. And then subtract that with ei of negative x. And then we add some arbitrary constant c. And of course I can just divide e to the negative x to both sides. So then that'll just leave us with f of x, and then that's equal to it's just equal to e to the power x ln of x, and then minus e to the x, and then ei of negative x, and then this is plus c multiplied with e to the x. I want to use the following condition. So let's say if I were to plug x equals 0, then the whole thing just becomes 0. So that's actually really nice. So let's see, use f of 0 equals 0. So then that means I would have to plug, so 0 is equal to e to the 0, which is just 1, or yeah, it's just 1. And then we have the natural log of 0. That doesn't exist. So what we have to do is actually write it in the form of a limit. So we'll say that this is approaching 0 from the right-hand side of the natural log of x. And then this is e to the 0 is just 1. Ei of 0 also doesn't exist. So we also have to write that in a form of a limit as well. So that means this is negative x. And then of course this is just plus c, it's still some arbitrary constant, so I'll just leave that out there. So now what we have to really do is evaluate this limit over here. Okay, so now this is where things get interesting. Okay, so well, we want to evaluate this limit over here, and then we could solve for our constant c. So now what I can do from here is that, let's see, I'll write this as the limit as x approaches 0 plus. Then what I can do is natural log of x, I can actually rewrite that as an integral, and our integral will be from between 1 to x of, let's say, 1 over t dt, right? And then plus, and then we're going to use the following definition that right over here. We're going to use the definition that the exponential function at x is actually equal to negative the integral from 0 to negative x of e to the negative t divided by t dt. Now, it was a minus, so I replaced the minus ei's of negative x using this definition, so that becomes a plus, but then using negative x over here, so that means that will become a positive x. So x and then to infinity of e to the negative t over t dt. Now from here, now I've written out the limit, what I can do is I can actually take the limit as x approaches 0, from the right, of course. So that means we have 1 to 0. We'll switch that, so that's a minus, and then this will go from 0 to infinity. Clearly, this is going to be the larger bounds of integration, so I'll set that to the front first and subtract it with this integral. So we have 0, infinity, e to the negative t divided by t dt. I subtract that with from 0 to 1 of 1 over t dt. And now next, what I can do is I can actually split this using the properties of adjacent intervals. So I'll split this into, so we're using the same integrand, of course, but I'll be splitting it with 2 different bounds. One is that I'm actually going to add the integrals together simply using one that starts from 1 to infinity of e to the minus t divided by t dt, and then plus the integral from 0 to 1 of the same integrand, t dt, and then of course this is still subtract with our 0 to 1 of 1 over t dt. Okay, now you'll see that for this integral over here, just going back to the definition, if I were to plug, let's say x is equal to -1, so that means this is following that definition, and so therefore this integral over here is actually just equal to the negative exponential integral at -1. And now next is to evaluate these integrals. So here, before I go further, let me write it like this, so I can actually combine these as one integral. I can combine these into one integral, since not only are they in the same bounds, but we can also, because we can combine it into one fraction since they share the same denominator. So therefore I can write this as this is 0 to 1 of 1 minus e to the negative t divided by t dt. Okay, so if I were to evaluate this integral, simply you can split this up into two integrals, just like from over there. Well, and then that will be a minus, so yeah, minus coming from over here, be minus, and then if I were to evaluate this integral, so I'll have, well, this is kind of a little bit difficult to integrate specifically. You know that 1 over t, the antiderivative of that is natural log of t, and if you were to plug in the bounds, obviously ln of 1 is 0, but ln of 0 does not exist, so you have to write it as a limit, and going through that calculation is even more work that we have to go through in this whole video. Same thing, so, and then the other one for e to the negative t, e to the power negative t divided by t, the same thing can be said, although if you were to plug 1 into there, so what's nice is that this will just be, let's see, ln of t, how about I write it like this, ln of t, and then minus e to the, so that's negative t, and then evaluate this from 0 to 1. What's nice is that if I just plug 1 into here, then these two will cancel each other out. However, you plug 0, you're going to have to write this in terms of limits, but I'm going to skip all that calculation. If you want to, I'm pretty sure there's actually a resource going through this whole derivation of integrating this. But what it comes down to is that this is actually going to equal to, well, I'll give you a straightforward answer. This is actually going to equal to negative ei of -1, and then plus lowercase gamma, where lowercase gamma is the Euler-Mascheroni constant. And since these two terms cancel each other out, and we have a minus gamma, so that means this whole thing is minus gamma. So then that would have to mean that this is going to equal, right like this. This is going to equal negative gamma, so therefore that would have to mean that our constant c has to equal gamma. So therefore, the following generalization is that f of x, can you see here? Yeah. You'll have to see that the following generalization that f of x is actually equal to, well, I'll restate that we have the infinite sum from n is equal to 1, and then h sub n, then x to the power n divided by n factorial. That's just equal to, this will just be, I can just factor out the, of course, the, where is it, e to the x. And so we have the natural log of x, then subtract that with ei of negative x, and then plus our Mascheroni constant, gamma. Okay, and now we're almost done. So of course we're given that we have to solve that the infinite sum is n is equal to 1 for h sub n and then n factorial. What I can do is I'll let x equals 1, and so therefore if I plug 1 to this entire thing, then we get that this is e to the 1, so, and then natural log of 1 is just 0, and then we have minus ei of negative 1, and then plus gamma. So therefore it's gamma. I'm just rearranging the terms. Let me write this gamma a little better. Gamma, and then minus ei of negative 1, like so. Oh, there we go. And our final answer is in this red box. That was a ton of work, if you ask me. and I had to skip some of the calculations, otherwise like for example these, otherwise it would take the video even longer than it should have. Alright then, so yeah, that's pretty cool if you ask me.